Welcome everyone. In this video lecture, we will discuss emitter follower circuit that is called the BJT Common Collector Configuration, and we will cover their AC analysis. So first of all, this one is the circuit diagram of a BJT Common Collector Configuration, or we can say the emitter follower circuit. Why it is called the BJT Common Collector Configuration? Because this collector terminal is common to both input and output when we are considering the AC analysis. And in addition to that, this circuit is called emitter follower circuit. Means if the input across the base side, okay, will be like this, okay. So it will follow the same, almost same output waveform or the same output side, that is our emitter side. So basically, output across the emitter, we can say the output across the side emitter side follows the input follows the input, okay, and both having in the same phase, okay, same, not 180-degree phase shift, okay. This is having the same phase, okay, and this, okay. And we can also say that this one is a common collector, because if we go for the AC analysis, this terminal will be common, okay. And V naught is somehow nearly same, okay, means nearly V naught equals to okay. So it is also used as a buffer, okay, but it has a high input impedance. It acts as a high input impedance and low low output impedance. So okay, so now we will go for the AC analysis. So the application is very simple. It is used as a buffer with high input impedance and low output impedance, and voltage gain is somehow equals to V in, or we can say voltage gain is always less than unity. So it will better to write, means this AV, it is our V naught by V in, is nearly equals to 1, but in ideally we can say it is less, means generally we are saying voltage gain is always less than unity. Here I am writing voltage gain, voltage gain will be less than unity, okay, will be practically less than unity. Then how we have to derive all these things, we will cover, okay. So so this is the circuit, emitter follower circuit, some basic idea I have already covered it, okay. So now we have to go for the AC analysis of that particular circuit, okay. So first of all, what we have to do for the AC analysis, the same circuit I am taking here, okay. So what we will do for the AC analysis part, what we will do, we have to re- discard the supply, okay. So if we remove the supply, it should be our grounded. In my earlier video I have covered so many times. And we have to short circuit the capacitor, okay. So I am just removing the capacitors now, okay. Okay, so now this one is the circuit. So this is our transistor, okay. Here also this the transistor, this one is our transistor, okay. And this transistor is nothing but simply what kind, N P NPN type, okay, NPN type. Now this one is the diagram, okay. Now we have to go for the AC analysis. So how to deal with this circuit, okay. So as we know, the how to draw the AC equivalent model for this transistor. So first of all, I am just drawing the AC equivalent model for this transistor. So this should be like, okay, this should be ground. Okay, so this one is our, once again I am just, this one I have made for the this base collector emitter side. Okay, so this should be our, simply we can say the R pi. Okay, and this one will be GM V pi, or somehow sometimes we can write as GM VBE, or this voltage is our V pi, or simply VBE, small VBE. Okay, for this transistor. Okay, and then after what we can say, this one. Okay, I am writing here, this one is our base side, collector side, and this side will be emitter, and we are taking output from this side, so make it V naught, and this one is our simply RE, so write it RE. Then after, this collector will be grounded, so make it ground, so collector will be grounded, so just make it ground. Okay, it is little bit tilted, but okay, it is grounded. Now this RB will come here. Okay, and this V in will be like this, plus or minus V in will be like this. Okay, and this R is grounded, so this one is our, basically you can say the V in, and this one will be RB and RE. Now this one is almost clear, means AC equivalent model for the emitter follower circuit. So this one we are drawing the AC equivalent model. So basically we are drawing what, AC equivalent model of emitter follower circuit. Okay, or say the BJT common collector, anything you can say. So this one is the diagram. Okay, so now this diagram is okay, means what we are doing, this transistor is replaced by R pi, all this thing. Now how to solve, we have to find the voltage gain. We have to find, for example, say voltage gain we are going to find first. Okay, voltage gain AV means V naught by V in, we have to find. So what we will do, one can easily say this current is our IB. Okay, AC current, so both symbol as well as the subscript will be in the small letter. This would be IC, and the current in this path will be IE, and this voltage is our simply V naught across this emitter side. So one can simply write V naught is simply IE times of RE. So what I am writing, V naught equals to I AC current, AC emitter current IE into RE. Okay. Now the IE is nothing but simply the base current plus collector current RE, means IB plus IC. Okay. Up to this it is clear. Then after, this one will be our V naught. Okay. Now again what we can write, IB. So this IB can be written as V pi by R pi. Is it okay or no? V pi by R pi. V pi by R pi plus IC is equal to simply GM V pi. It is very simple. In my earlier video, I have covered this one so many times. Means here this resistance is there. Is R pi. Some current is flowing IB, and this potential is V pi. So current in this one IB will be this potential across this resistor by R pi. Okay. Now this IC is same as that of this one is current source. So GM V pi. So we can write like this. Okay. Very simple calculation is there, but practice you have to do. Then 1 by R pi plus GM. Okay. GM. If we take common V pi from these two terms, we can write it RE. Okay. Now I am going for one simplification that it should be GM V pi RE, because I am writing 1 by R pi is very less than GM. Okay, because the R pi, that is our 1 by beta by GM. Okay, so it should be around GM by beta. So GM by beta is a higher quantity like 100 to 500. So and GM, so this will be very smaller than GM. So we can remove this term, okay, to 0. Okay, so this one R pi we know, beta by GM. Okay, so that thing I have put it here. Okay, clear. So this can be somehow equals to GM V pi RE. So I am highlighting this term. V naught equals to V pi or GM V pi RE. Okay. Now V naught is somehow clear. Now we have to introduce V in. So what we can do, we can go for Kirchhoff's voltage law in this loop. Okay. Say loop from this side to this side. Okay, to this loop. Okay, so one, so by I am writing applying KVL in loop 1, say. Okay, so what we can write, simply one can write plus V in, plus V in minus V pi equals to VB minus V pi, and this voltage is V naught. So we can write simply V naught equals to 0. Very simple observation is there. Then after what we can write, V naught equals to simply V in minus V pi. V naught we have put here. Okay, so V in minus V pi. Now V naught equals to V in minus V pi. Okay, so it should be V in and V pi. From here we can write V pi equals to V naught by GMRE. From this one we can write. So if you put here V naught by GMRE. Okay, we are taking this. Okay, V pi from this equation, or we can say this one equation number 1, or okay, or equation number anything. Okay, so now what we will do, now V naught V in each two terms are there, then V naught can be written as 1 plus 1 by G R E. Okay, oh, GM R E equals to V in. Okay, so the gain will be very simple, V naught by V in equals to what we can write, 1 by 1 plus 1 by GM RE. Okay, or this expression can be written as GM RE by GM RE plus 1. Okay, or one can do like this, GM RE I am writing here, and also we can take GM common here, so RE plus 1 by GM. Okay, if I am taking GM common, it should be RE plus 1 by GM. Okay, so this should be cancel out. So this one will be also one of the expression we can say, RE by RE plus 1 by GM. Okay, this one or we can simply remember GM RE by GM plus RE. Okay, so GM RE is somehow much greater than 1. GM RE will be greater than 1. Okay, so this value is nearly equals to 1. Okay, clear this one. So this V naught by V in, it's simply we can write here V naught by V in, one can write GM RE by 1 plus GM RE, which is equals to 1. Okay, so this one is a very important result. Okay, which is called our gain. Okay, and this is the is used as a emitter follower. Okay, emitter follower, because input follows the input, because V naught is somehow equals to input voltage. Okay, so for remember the gain means this, from this expression one can also write V naught equals to GM RE by 1 plus GM RE into V in. Okay, so why I am writing this one, or we can write this as a RE by RE plus 1 by GM. Why I am writing this into V in? Simply V naught by Vi. So now, so what we can do, we can write like that. This circuit, for this one, if this one is our V input, okay, there will be 1 by GM and RE. So this one V naught equals to V in into RE, voltage division rule, by RE plus 1 by GM. So V naught. Okay, so that's why we are writing like this for voltage division rule. That's why this GM come here and RE will be come here. So V naught equals to V in RE by RE plus G1. This one is a Thevenin equivalent circuit seen from the emitter side. We can say this one is the Thevenin equivalent circuit. I am writing here. Okay. Thevenin equivalent circuit looking from the emitter side. Okay, so this one is simple, the gain calculation. Now very simply, from this circuit, okay, from this circuit I am making here, this one is 1 by GM and this one is RE. If we ground the input for output impedance calculation, I am doing for the output impedance. Okay, for the output impedance calculation, we have to make it ground. V in is ground, and this should be the output impedance. Okay, so Z naught will be very simply, please find out RE parallel with 1 by GM. So this is the output impedance calculation. This one is the output impedance calculation. This one is the gain. Okay, and this one is the Thevenin equivalent circuit looking from the emitter side. Is this one. Okay, from these two circuits, we can find easily the output impedance and voltage gain V naught GM RE by this. Okay, we can also find the output impedance using the traditional method. Okay, so I will also try to make the output impedance using the traditional method. Okay, so what we have to do, output impedance calculation using the traditional method. Output impedance calculation. Okay, means using the traditional method. So for that thing, again I have to make the equivalent AC model. Okay, this one is our GMV pi, this one is R pi, this one is RE. Okay, this would be our grounded RB, and this should be our grounded, because for the output impedance we are taking V in 0, or we are making the it is ground. Okay, and we are putting a voltage source, that is our VT, and some test current IT in the circuit, and this current is simply our IB, IC. Okay, clear. So basically the input impedance looking from this side, that is our Z naught. So this Z naught will be simply our VT by IT. So what we have to do? So as we know, this one is our base, collector, and emitter side. So there may be some current are going through this point. Okay. So by applying KCL, okay, I am writing here. By applying KCL at E point, that is our emitter point, at E point. Okay, and this current is called our what we can say, the IE current. Okay, means this one is the circuit, very simple. Okay, so what we can say, the current, okay, the current IB is nothing but simply this voltage VP. So I can write at this point, we can write IB plus IC plus IT, total incoming current. IT, better I'm written capital IT. Okay, better to write capital IT. Simple KCL IT, total incoming current equals to total uh, this current. Okay, that is our IE. Means now these two current IB, IC, IT, then IE. Now what we can write, IB value. IB value is nothing but simply V pi by R pi. Very simple. IC can be written as GM V pi. IT is IT. Okay, no need to worry. And IE. So this potential is VT. So VT by RE. So it should be our VT by RE, because this one is RE resistance and this potential is VT. So the IE current will be VT by RE. Simple. Okay. So now we have to observe what is the relationship between V pi and VT. So one more observation is that if we apply Kirchhoff's voltage law in this loop, okay, say loop one can write minus V pi minus Vt equals to 0. So Vt is same as that of V pi with negative sign. Very simple. Vt equals to minus V pi. Okay, very simple. This one is 0 potential, so no need. Minus V pi and minus Vt equals to 0 by applying KVL. Okay. So instead of V pi, we can write minus Vt. Okay. So I am writing here minus Vt by R pi minus GMVT plus IT equals to Vt by Re. Okay. Now put Vt in one side. So if we put, it will come Re1 by Re plus 1 by R pi plus Gm. Okay. Equals to It. So here Vt by It, that is our simply Z naught we can say. This will be, and I am neglecting this 1 by rp is somehow 0. 1 by rp beta by gm. Okay, so very negligible value. Earlier 1 by r pi beta by gm. Oh sorry, beta by gm. Okay, 1 by r pi beta, oh beta by, okay, 1 by r pi beta by gm. So gm by beta, it is very less. What is gm? So we are neglecting this part. So z naught will be v naught 1 by re plus gm. Okay, and this can be also written as, if we put re in the up, then it should be written as 1 plus gm re. Okay, so one more line we can write. So z naught, and if we take re common, so make it, sorry, gm common, so one can write 1 by, okay, 1 by gm plus re. Okay, if we take gm common, so 1 by gm plus, it should be re, so it is written as re into 1 by gm by re plus 1 by gm. So r1 r2 by r1 plus r2. So our z naught is simply re parallel with 1 by gm that we have already derived. Okay, so this one is the z naught. Okay, av, the av value we have calculated, av gm re by gm re plus 1. Okay, this one also we have calculated. Okay, okay, one more thing is still left, input impedance. So it is very simple, means by using this expression KCL at point E, we have derived, means this value is gm re. Okay, we can write like this. So this is simply our impedance, output impedance, through a traditional method we can find. Okay, now input impedance, one more thing is still left, so it will better to cover. Okay, input impedance, input impedance. Okay, so once again, for the input impedance, we can go for this circuit. Okay, I will make the circuit. Okay, so again we have to do the same thing. For the input impedance, we have to make the circuit. Okay, a small signal model circuit. Okay, so every time you have to do this one. Okay, re, this should be grounded, gm v pi, this should be our rb. Now in this time there is no need to remove the v in, and this will be our r pi, and this will be our v pi. Okay, re, and no need to disturb v naught. Okay, so in this time input impedance, make it the output will be somehow 0. Okay, so what we can do, this value is our z input. Okay, so now this impedance is, say I am saying zb from this side, so z in will be simply rb parallel with zb. Okay, clear? Z in is nothing but simply rb parallel with zb. Okay, so now what we can do, we can do this zb, we have to find the value of zb. So zb, we can say this one is, say, our v in, or I am saying this one is vb. So we can say vb by ib. If we are able to find vb by IB. Okay, so then we can easily say what should VB by IB. Okay, so now what we can do, this VB, okay, or this V pi can be found by using, okay, say this one is the output one, and say this voltage is VE. So this VB potential we have to find. So what we can do, not make it ground now. So V in minus V pi minus VE equals to 0. So V in is nothing but simply our VB. Okay, so V pi plus VE, and V pi is IB into R pi. IB into R pi, and VE is nothing but simply beta plus 1 IB RE, because this current will be IB plus IC. Okay, IB plus IC. So IB plus beta IB. So beta plus 1 IB into RE. So that's why I'm writing like this. So this VB by IB will be R pi plus beta plus 1 RE. So VB by IB. Now this impedance will be, so this overall impedance will be R pi plus beta plus 1 RE. So this one is the input impedance calculation for this common collector configuration. So now summary. Okay. Now we will write the all the calculation that we have observed as a summary, and even okay, here I am writing as a summary. Okay, means the input impedance in a common collector configuration is RB parallel with R pi plus beta plus 1 RE. Okay, Z naught we have already find 1 by GM parallel with RE. Okay, in the very first slide we have calculated Z naught RE parallel with GM. Okay, RE parallel with 1 by GM, and one more thing. Okay, AV GM RE by 1 plus GM RE. Okay, so without, and this one without R naught, but when with R naught, here I am writing with R naught, means when we are considering finite output resistance, finite output resistance, we have not taken the finite output resistance R naught, but when we will consider this one, so the our Z in will be our RB parallel with R pi plus beta plus 1 RE parallel with R naught. Okay, in RE we have to make it parallel, and Z naught will be 1 by GM parallel with RE parallel with R naught, and AV GM, okay, or we can GM RE parallel with R naught by 1 plus GM RE parallel with R naught, or one can write like this: RE parallel with R naught, okay, 1 by GM plus RE parallel with R naught. So these are the very important observation, okay, for the common collector configuration or common sorry, emitter follower circuit, where input follows the output, input across the what we can say, the base side, it follow the output, input follows the output, and it used as a buffer. Okay, clear. So this is all about the mm, SE analysis for a emitter follower circuit or BJT Common Collector Configuration. So thank you for watching this video. You can go step by step. It will take some time, but after some practice, it will more clear how it is coming. So thank you for watching this video.